This is a tutorial on evaluating logarithms. A logarithm, or a log, is basically the inverse function of an exponential function. Here, if I have log base b of y, and that's equal to x, then I can rewrite this log expression as y is equal to b to the x. My base stays the same, and all we're doing is switching the location of our y and our x. Logs are useful when we want to pull a variable out of an exponent. And these always work as long as our b is positive or greater than 0 and our b is not equal to 1. If our b was equal to 1 and we went back to this exponential function, we would have y is equal to 1 to the x. And this would be 1 times 1 times 1 x amount of times. And 1 times 1 is always 1, so it wouldn't matter what x is equal to. This would always be equal to 1. So that's why b cannot be equal to 1. But whenever you see a log expression, you can always just rewrite it as an exponential expression. So if I have 27 is equal to 3 cubed, which it is, then I could rewrite that as log base 3 of 27 is equal to 3. Notice the base of our exponential and the base of our log is the same. And the only thing that changes position is the 27 and the exponent. Again, here I have 64 is equal to 8 squared. Well, I can rewrite that as log base 8 of 64 is equal to 2. They both mean the same thing. Now, frequently, you'll see log written without a base. Here we have y is equal to the log of x. A calculator with a log button on it usually does not have a base for that log. If you ever see a log that doesn't have a base on it, that means the base is 10. This is called the common log, or the common logarithm. So again, whenever you see a log without a base, that always means that that base is 10. So if we had written log of 7, that always means that the log base 10 of 7. So now let's talk about how we can evaluate logarithms. Here we're told that the log base 10 of 100 is equal to x. And if we wanted to solve this for x, I would have to rewrite this logarithm as an exponential expression. Remember, I can write log base 10 of 100 equal to x. This means 10 to the x is equal to 100. Now, 100, that's 10 squared. So that means 10 to the x is equal to 10 squared. And since our bases are the same, they're both 10, that means x has to be equal to 2. So that means that the log base 10 of 100 is equal to 2. Let's try this again. Here we have log base 3 of 81 is equal to x. And if I wanted to solve this for x, I would rewrite this as 3 to the x is equal to 81. Now 81, that's equal to 3 to the 4th power. So if we have 3 to the x is equal to 3 to the 4th power, that means x has to equal 4. So the log base 3 of 81 would be equal to 4. Now let's talk about the domain of logarithmic functions. Here we're told that the log base 5 of negative 2 is equal to something. Well, I'm going to rewrite this as the log base 5 of negative 2 is equal to x. If I write this way, then I can rewrite this as 5 to the x power is equal to negative 2. Now let's look at this left-hand side. Here we have 5 to the x. This is the same as 5 times 5 times 5, x amount of times. If x was negative, this would be 1/5 times 1/5 times 1/5, a negative x amount of times. But either way, we're always multiplying a positive number by a positive number. Because we're always multiplying a positive number by a positive number, there's no way that we can get a negative number out of this. There is no value of x that can give us a negative 2. That means that the log base 5 of negative 2 is undefined. Let's look at our next example here. We have log base 10 of 0 is equal to some number. Well, again, I'm going to call this log base 10 of 0 is equal to x. And if I can write that, that means 10 to the x is equal to 0. Now, once again, let's look at this left-hand side. This is 10 to the x. So if x is positive, this is just 10 times 10 times 10 x amount of times. If x is negative, it would be 1/10 times 1/10 times 1/10, a negative x amount of times. If x was 0, this would be 10 to the 0, and that's equal to 1. So there's no number that we can plug in for x that would make 10 to the x equal to 0. The only way I can multiply 10 by anything and get 0 is if I multiply it by 0. So therefore, the log base 10 of 0 is also undefined. Whenever you take the log of a number, that number has to be greater than 0. If I'm taking the log base b of x, x has to be greater than 0. Otherwise, my log function is undefined. Now let's try graphing a logarithmic function. And let's compare it to the exponential function. Here I have y is equal to 2 to the x. And you can think of this as the log base 2 of y is equal to x. Now if I want to graph y is equal to 2 to the x, I need to pick some x values. And I'll pick negative 1, 0, 1, 2, and 3. If I plug them into this equation here, y is equal to 2 to the x, well, I'll have y is equal to 2 to the negative 1. That's equal to 1/2. I'll have y is equal to 2 to the 0. That's equal to 1. Y is equal to 2 to the first power. That's equal to 2. We'll have y is equal to 2 to the second power. That's equal to 4. And y is equal to 2 to the third power. And that's equal to 8. If I plot these points, negative 1, 1/2 is right there. 0, 1, 1, 2, 2 and 4, and 3 and 8. Connect them with a smooth curve. And the graph of y is equal to 2 to the x would look something like that. Now let's graph the function y is equal to log base 2 of x. The easiest way to graph y is equal to the log base 2 of x would be to rewrite this as 2 to the y is equal to x. Now I'm going to select some y values, and the y values I'm going to select are going to be negative 1, 0, 1, 2, and 3. If I plug these in for y, I should be able to get my x values. First, I'll have 2 to the negative 1. Well, that's equal to 1/2, so my x would be 1/2. If I plug in 0 for y, I'll have 2 to the 0, and that's equal to 1, so my x will be equal to 1. If I plug in 1 for y, I'll have 2 to the first power, and that's equal to 2. So my x would be 2. Next, I'm going to plug in 2 for y. I'll have 2 squared. That's equal to 4. And then lastly, I plug in 3 for y. I'll have 2 cubed, and that's equal to 8. Now I can plot these points. X is equal to 1/2, and y is equal to negative 1. Well, that's right there. 1, 0 is right there. 2 and 1. 4 and 2. And 8 and 3. Connect these with a smooth curve. And the graph of y is equal to the log base 2 of x should look something like that. And notice that these two graphs are reflected across the line y is equal to x. And notice before, when I rewrote y is equal to 2 to the x into logarithmic form, we had log base 2 of y is equal to x. Well, my other function here is y is equal to log base 2 of x. So these two functions here are inverses of one another. Now let's talk about translating logarithmic graphs. Here we have the standard form for a translation. This is y is equal to the log base b of x minus h plus k. In black, we have graphed here y is equal to log base 10 of x. Notice it has an asymptote, that is the y-axis, because you cannot take the log of a negative number and you can't take the log of 0. So our graph can never cross the y-axis because that would make x equal to 0. And if I wanted to translate this horizontally, well, that occurs in our blue line here. We have y is equal to log base 10 of x minus 2. This, from the original graph, is a horizontal translation in the positive direction of 2. That's because I have a minus 2 inside the log function. In red here, I have the log base 10 of x minus 2. This minus 2 is outside of my log function. And that gives us a vertical translation down 2. Well, if you look at our base form here, y is equal to the log base b of x minus h plus k, our h is our horizontal translation. In blue here, it was minus 2, and that gave us a positive 2 horizontal translation. Our k, when it's outside of the log function, that is our vertical translation. Here, our k was a negative 2, so our graph was translated down 2. So that's how you can translate logarithmic graphs. If you want a horizontal translation, you have to put it inside the log function. And if you want a vertical one, you add or subtract a constant on the outside of the log function. And that completes the tutorial on evaluating logarithms.